All right, hi everyone. We'll get started. How are we doing? Good. How did exam one go? Ish. Okay, some okay, some middles all around. I'm grading some of that, so I think both professors will have it in a week, like after you took it. Just because they have a makeup on Friday, and then we just need to kind of finish everything up in that way. So I don't really know what's they're grading a lot of it. I'm grading a lot of it, so I don't really know what the distribution is right now. But yeah, that'll be next week. Is there anything from exam one that y'all have questions on? Not like specifically the exam, because we can't talk about that yet, but like any topics or something, or we just gotta focus on the next one? Next one? Okay, perfect. So what do we want to see today? Gas laws? Yeah. Mostly PIV PV equals nRT. Yes. Yeah. Okay. I feel like that's the big thing that we're talking about right now. So when we talk about gas laws, the ideal gas law, right, or how we expect gases to behave is what equation? It's going to be given to you, but what is it? PV is equal to nRT. Good. Okay. And just to quickly go through what this is, what is P? What does that stand for? That's pressure. And what unit is that usually in? Good. What about the V? Volume. And that's in liters. What is N? That's moles. What is T? Temperature. And what unit is that in? Good. And what is R? That's your constant. Yep. And that's 0.08206. And this constant will be given to you as well, but in case you need to know what one you're using for a question, because both will be given at the same time, right? That's going to be based off of all of the other units that you're working with your gas. So that's going to be liters times ATM over moles times Kelvin. Okay, so you can see that all of the other units that we have in parentheses is also in our gas constant unit. So that would all cancel out at the very end. Okay. Any questions on just the setup of PIV-NERT? Okay. PIV-NERT is fun. It comes into play a lot. And it's also fun to say. But there are also two different variations of PIV-NERT that we can talk about. One involves density and one involves the molar mass of a compound. Does anyone know what those are in terms of what PIV-NERT turns into, or like how we rearrange it? I think so. No, not that one. So if we're talking about molar mass, so what are the units of molar mass? Grams per mole. Yep. Okay. So if we're given grams of something, or we're given the identity of a gas, you can use molar mass in your PV is equal to nRT equation. Usually you're going to find something where you might be asked for the identity of a gas. So right, we said we have pressure volume is equal to moles RT. So your N here is in moles. Right, and that's going to be this mole component here, right? So you're able to substitute in and rearrange in order to rearrange PIV-NERT so that you can find for the identity of a gas. Let me have a couple questions. Yeah. So it turns into PV is equal to the mass over the molar mass times RT. That way. Because N is moles. Oops. Ignore my periodic table. Lovely. M is mass. And big M is molar mass. I think that one will be given to you, but in case you do need to plug that in, right? Or know it right away, there's that one. And then if we're looking at density, what are the units of density? Mass over volume, yep. So volume comes into play with your V component of your PV is equal to nRT. So if you rearrange that a little bit, you can get that the density of an element or a density of a gas is equal to M as in mass again, times pressure divided by nRT. And that would give you pressure, and that would give you your density of your gas. So if we're looking, right, we know that density is going to be mass or little m over volume, which is big V. CFPV is equal to nRT as your initial starting bit. We know that N is going to be moles, right? And we just said that N is going to be equal to mass over your molar mass, okay? So then we know that we want to substitute mass over volume someplace in this. So we can first plug in PV is equal to mass RT times molar mass. And then if we multiply molar mass on both sides, PV times molar mass is equal to mass RT. Then we can divide by volume on both sides. So P times molar mass is equal to MRT over V. This now turns into this up here, which is our density. So pressure times the molar mass is equal to density RT. And we divide by RT on both sides to get density by itself. So then this turns into either density is equal to pressure times molar mass over RT, or the mass, right, rearrange that initial one that we gave you. But those are the two versions of that one, and that's how you would solve it. It's a lot of rearranging and yada, yada, yada. So I like to give you the simpler version better. Does that make sense how we got to like kind of derive that? You don't need to know how to derive it, but in case you do need, if you forget, right, and you want to solve for it, that's how you would be to do it, and you can solve it somehow. Again, you just want to keep track of your units along the way. But I do have to say one thing about, I know iCloud. One thing about exam 1 is that you, I see a lot of problems with following units or canceling out of units. I think it's super important, especially right now, while you're practicing these new equations, to always include units with your numbers that you're using. You might be able to drop them on your exam because you know how to use them. But I see just a lot of mistakes so far of things not canceling out, or maybe you're multiplying moles by moles, and so you get moles squared, but you don't realize that. So having a roadmap of units is super helpful, and it will kind of be a red flag, right? Or something that'll jump out to you if you're not seeing something cancel out as it should. So I always like to give these types of problems just so that you are using units more often. Okay, any questions on PV is equal to nRT so far and the different variations? It'll be like based off what's given to you in your question. So, right, it might ask you for the identity of a gas that has a specific density. If you're looking for the identity of a gas, the best way to identify a gas is through its molar mass. So then that last one in the corner is probably easiest because you can identify the molar mass right away once you rearrange it again. But sometimes you might be given, right, grams, and you need to find, like, in your given density, you want to find the volume of what that is or something like that. So then it's easier to use the mass that way because then you have the mass directly and you don't need to worry about the molar mass. But it's just kind of dependent on what is given to you in your question. You want to practice a couple PV. Yep, so for this question, right, we have a gas occupies a volume of 12.3 liters at 25.0 degrees Celsius and a pressure of 755 millimeters of mercury. How many moles of the gas are present? Is this something we want to try or work on together? You want to try it? Yeah, I can give you all a couple minutes, get started and try it out. If you have a question, don't know where to start, raise your hand. Yeah. Yes, yep. Yeah, so kind of go reference back to that initial like breakdown of PV equals nRT that we talked about, see what units need to be changed, if any. Bless you. And then help you out. Yep.
For R, does the value ever change?
For gases or like in general? So there's two versions of R. There's the 0.08206 that we use for gas laws. And then there was 8.314, but that's in joules per mole Kelvin. So that's an energy unit. So you'll use that more in thermodynamics. And like enthalpy and energy related stuff. So when you talk about gases and gas properties, and you're talking about pressures and volumes and temperature that way, then you're going to use the smaller version. You can convert those units into joules, and that's where you get the 8.314. And that's when you use it, is when you're in energy. Yep. So if you're looking for the energy of something, then you want to use the bigger number. But if you're talking about gases, then you want to use a smaller number. Great question. Did anyone get an answer for the number of moles? Yep. Y'all want to tell me what you did?
We'll divide 755 and 760 to get the ATM, which was 0.993
Awesome.
ATM. Multiplied by 12.3 liters, and that's already for.
Yep. And then we know that we're going to be using PV is equal to nRT. So we changed our pressure because that needed to be in different units. You said 0.993, right? Our volume given to us in liters already. So we can keep that the same. Then what'd you do?
And
Mhm.
just the variable, put constant on. And then Celsius and Kelvin already 223 to 15 to 25.
Mhm.
Now turn on the 8.15. And then multiply the right hand side and divide it.
Beautiful. Yep. So once you set up PV is equal to nRT, you should have these values plugged in. You're more than welcome to rearrange PV is equal to nRT when you want to, right? If you wanted to say, okay, I'm solving for n, and so the first thing we did was divided by RT to be left with n by yourself. Totally fine, right? Then you can plug it in that way. Totally up to you. It's all multiplication division. It doesn't really matter too much in terms of PEMDAS, as long as you just rearrange it correctly. But right, you have PV and then multiply that together. You can multiply RT together and then divide the other, divide PV divided by RT. So I end up with 0.4999678. And how many? Oh, 1, 2, 3. And how many sig figs would we need here? By 3.
And the smallest that we're given is like the 12.3 is like the smallest. But I know it's like the
Nope. So
like this guy.
yes, perfect. Right. So if we talk about everything, I like that we wrote it this way, right? The one addition that we really did here was our 25.0 plus 273.15. Your conversion factors or your constants, right? K being a constant, or K being conversion factor, or 760 millimeters of mercury being conversion factor, those are infinitely significant, right? So it doesn't matter how many significant figures are in those, we just take those as infinitely significant. They don't count towards it. So you want to go based off of essentially how many sig figs you have in your original question. So in your original question, we're given 12.3, which has how many sig figs? 3. We have 25.0, which has how many sig figs? Also 3, and then we have 750 millimeters of mercury, which has how many sig figs? 3, right? So this one's pretty straightforward. All of them have 3. And so at the very end, you want to round to 3 sig figs as well. So I'm gonna have 0. What? 500, perfect. Questions on this one? Right, so now I could say, right, you're given moles and you had, oops. If I asked you for the molar mass of the sample, how would we go about solving that now that we know it's moles? So let's say we've already solved it. We already know that we have the 0.5. What's the easiest way to get to our molar mass? Perfect. Yep. Right. We know that molar mass is going to be grams per mole. So we can just plug in our 3.2 grams over our 0.5. We'll end up with 6.4 grams per mole. And lithium is equal to 6.94 grams per mole. So if I was smart, I would give you like 3.4. But right, it would be like about lithium, right? You look at your periodic table once you found your molar mass and say, okay, this is probably going to be lithium gas. That's in my sample. Does that make sense how you would solve for like identify the gas type of question? What other questions do we have about PV is equal to nRT? Okay, do we have any other gas questions in general? Problem? Yeah, absolutely. Let me pull one up. Any questions on this one before I move on to? Okay, so for this one, we have an ideal gas has a density of 1.17 times 10⁻⁶ grams per centimeters cubed at 1 times 10⁻³ atm and 60 degrees Celsius. What is the identity of the gas? This is another one we want to try on our own a little bit, get started. Yeah. Okay. Look back at the density one we just solved for. Bless you. And then. Need to pay at the table. Bless you. Did anyone get an element? Okay. Is anyone stuck? It's okay to be stuck. Do you want to start going? So what's the first thing we did in order to solve this question? Or what do we already know? Awesome. So we know that density is going to be 1.17 times 10 to the negative 6 grams per centimeters cubed. Is that in units that we like to work in? No. So what do we need to do to that first? We need to convert this into what units? We need to do it from centimeters cubed to liters. Yep, so we'll have 1.17 times 10 to the negative 6 grams over centimeters cubed. We're given that 1,000 centimeters cubed is equal to 1 liter. So we can say 1,000 centimeters cubed divided by 1 liter is going to be 1.17 times 10 to the negative 3 grams per liter. Okay, and now that's in units that we like, because these will cancel out. Any questions on changing centimeters cubed to liters? Okay. What else do we need to change? Good. And how do we change temperature into Kelvin? Awesome. We had 273.15, and so we end up with 333.15. And that's in Kelvin. Everything else look okay after that? Looks good to me, right? So we know that we have density is equal to pressure times molar mass divided by RT. We're solving for that molar mass. And so we said density was 1.17 times 10 to the negative 3 grams over liter. Pressure we said was 1.00 times 10 to the negative 3 atm. We don't know our molar mass. And then we'll have 0.08206 liters atm mole Kelvin. And temperature was 333.15 Kelvin. Okay, and again, you can solve multiplication, division, whatever, right? Get a common denominator, cross multiply, divide, whatever you want to do that way. What do we end up for a molar mass?
I have the answer, 31 something.
Mhm.
Okay.
Yeah,
31,
yeah.
95. 31.98. I guess it's
Perfect. And that will say 9 grams per mole. And it'll be more than one time that I'm going to tell you all the wrong answer and you're going to have the correct one, so it's totally fine. Okay, so we end up with 31.99-ish grams per mole, which is about 32 grams per mole, right? So if we look at our periodic table, does anyone know it has a molar mass of 32? Can anyone see that? I know I wouldn't. Point you in the right direction. It's over here.
Sulfur.
Yep, sulfur has about 32. So sulfur could be a potential answer. One thing about this type of the periodic table is interesting is that your oxygen, right, your nitrogen, oxygen, fluorine, and chlorine, all of those are in red. And what else is in red? Your noble gases. So what phase do we think oxygen is in? Gaseous phase. What do we think sulfur is in? Not a gaseous phase. Right? What else do we know about oxygen? What is it usually looking at? It's diatomic, good. So if we have two oxygens, what's the molar mass of oxygen? 32, right? So this one, for this particular question, your answer is going to be oxygen, but I would have accepted sulfur too, because you just looked at your periodic table. Yep, so for this one, this question is actually oxygen, but oxygen, sulfur, I'm going to take either one of them. Just happy you're participating. But it's oxygen because it's diatomic, but I would also accept sulfur.
You said this earlier, but
Yep.
you gave us two formulas for density. How would you know when to use?
Kind of depending on how the question is asked, right? So for this one, we're asking for the identity of a gas. And so the one that directly gives us a molar mass is easiest to use because that's going to be the easiest way to identify a gas. But if you're looking for not the identity of a gas, then the other one might be a little bit easier to use because then you can solve for grams or liters directly from that one. Yep.
Which the one that has, the one where we're finding the mass
Mm-hmm.
does have moles in the denominator?
Yes, I believe so. Yep. I prefer to just use the one given here. You're gonna memorize one equation. I think that's the one given, or I think that's the one to know over the other one. So I would just say stick with this one, and that would be fine. Any other questions? Okay, what else from gases? How do you feel about all of like the kinetic molecular theory and whatnot? Go over a little bit of that. Yep. Alrighty. So when we talk about kinetic molecular theory, this is again referring to ideal gases, right? Is what we're mostly going to be looking at. I know, did y'all talk about non-ideal gases today? Maybe we might not have. It was like the very end of chapter 5. I think you might have covered it. But in terms of like non-ideal gases, you don't need to know how to do any calculations for those. You just need to know the differences in properties between an ideal and a non-ideal gas. So to kind of go over what makes an ideal gas, what kind of pressures do we like? Do we like gases to be at high pressures or low pressures? Low pressures, yep. Because if we talk about a high pressure, right, that's like taking gas particles and squeezing them really close together, right? And if they're really, really close together, then they start getting some of that elastic collisions and they could start forming a solid, or a liquid first and then a solid. So at low pressures, right, that's because it gives a lot of open space, right? They have a lot of ability to move around. There's not that elastic collisions and some of your intermolecular forces are not taking over. So low pressures are ideal for gases. What about temperature? What do we like for temperature? High temperatures, yep. And high temperatures make sense, right, too. Right, when you want to boil water, do you turn your stove off or do you turn your stove on? You turn it on, right? You need to heat things up in order to make them into gaseous particles. So the higher the temperature, the more gas-like they are, and that's good for ideal behavior. And then what about volume? Do you want low volumes or high volumes? Also high, right? right? And when we look at our properties here, this makes sense according to our PV equals nRT. What kind of relationship does pressure and volume have? They have an inverse relationship. So at low pressures, we're going to have high volumes. And so if we have an ideal behavior, that low pressure, high volume combination is going to be very ideal. And then what kind of relationship do we have between volume and temperature? They are proportional, right? They're directly proportional. And so when we look at high volume, we also could have high temperature, or higher temperature means higher volume. And so that all makes sense according to PV equals nRT. These are all ideal conditions, and that's why PV equals nRT works. When else we talk about kinetic molecular theory, we also talk about our average speed of particles or your gases, right, to temperature. So does anyone know one version of the kinetic energy equation? There's two different types. There's like a physics one and then a temperature one. Say it again. Yep, yep. So we know that kinetic energy is equal to 1/2 mv squared, right? Where v is your velocity. I call this one my physics kinetics equation. And then we can also relate temperature, where kinetic energy is equal to 3/2 RT. These are provided. Yep. The physics one, you might just memorize over time over uses. I hardly ever use the 3/2 1T outside of right now. So when we look at this, right, we can say that these are both kinetic energies, and so we can set them equal to each other. So your 1/2 mv squared is going to be equal to 3/2 RT. And with a little rearrangement, we see that your velocity, right, again, the speed of which your particles are moving, is related to 3 RT divided by its molar mass. And so what kind of relationship does velocity and molar mass have? I think that's correct. So the smaller the molar mass, the slower or faster the velocity. The faster the velocity, yep. Right, if we think about this in terms of actual numbers, the smaller your denominator is, the bigger the number actually becomes, right? If we look at 1/2, this is 0.5. And if we look at 1/4, this is 0.25. So as our denominator gets bigger, our numerator, I guess, your decimal point gets smaller, right? So those are inversely related. So the smaller your molar mass, the faster it's going to be moving. Average, on average. What R would we use in this case? We're talking about energies, the higher one, right? This R here is 8.314 joules over mole Kelvin, because now we start talking about kinetic energy. We're in an energy kind of state of mind. And that means that we need to use energy units, which is that joule or that J in our unit. Right, and again, this is all the average of something, but the big idea here is that the smaller the molar mass, the faster the velocity, the average velocity of the particle. Mhm. Um,
What does it say, moles over what?
Moles over hour, it's like each, yep. Hmm. All right, so for this question, we have a sample of oxygen, O2, has a rate of 7.33 times 10 to the negative six moles per hour. And an unknown gas under the same conditions has a rate of 4.25 times 10 to the negative 6 moles per hour. What is the molar mass of the unknown gas? So I gave you a question with the intention of using a formula that we didn't really talk about too much. Does anyone know what formula we would use in order to solve? Awesome, yep. So we have rate 1 over rate 2 equal to the square root of molar mass 2 over molar mass 1. Right, and this comes from that velocity equation that we were talking about. Right, we could say that velocity, which is also equal to rate, is 3 RT over molar mass. Right, then we can call this 1 and 1. And then we can have rate 2, which is 3 RT over molar mass 2. So if we just divided these, all the common stuff cancels out. And so we end up with rate 1 over rate 2 equal to the square root of 1 over molar mass 1 over 1 over molar mass 2, which ends up being this guy here once you keep change flip your fractions. But I don't remember if this one's given to you, but if you do have to memorize this equation, rate 1 over rate 2, if you just remember 1 and 2, and then you know that you have to flip and have an inverse of the other one, right? 1, 2, 2, 1 in terms of your equation. Okay, so why don't you all try and solve the rest of this? See if you can find the molar mass of your gas. Anyone get a molar mass? What'd you get?
95.
Yeah, 95. Awesome. Yep, so I got that our rate, or sorry, our molar mass 2 in this case would be 95 point, how many sig figs? Yeah, so 95.2 grams per mole. Okay, and how we just set this up. We said that this was 7.33 times 10 to negative 6 over 4.25 times 10 to negative 6. Sometimes I just write in parentheses like what that's for, right? So this is for my oxygen gas and this is for my unknown, right? So I kind of keep track of what it is. And then I'll have my molar mass and my molar mass 2. What I'm solving for, because my rate 2 is on the bottom, I need to put my unknown mass of my rate on the top of my right-hand side of my equation. And then again, oxygen is diatomic, so we need 2 oxygen molecules. So that's going to be 32.00 grams-ish per mole for our molar mass of oxygen. And then you can plug and chug from there. Any questions on rate? Does that help with a little bit of that stuff? Okay, and then I think just in our last minute, I'll just briefly just talk about a Boltzmann distribution. There's 2 ways that you can see a Boltzmann distribution. You can see temperature on this side, I think it is. I don't want you to, I don't want to tell you the wrong thing. Yeah. I could tell you number of molecules. And I can tell you average speed. And if I tell you that it looks like this, or it looks like this, and I say that nitrogen 2 is at 25 degrees Celsius, and that 2 is at 100 degrees Celsius. Can you tell me which one belongs to which? Flatter one is the hotter one. Yes, yep. N2 at 100 is going to be your flatter one, because we have more molecules at a higher speed, right? The higher the temperature, the faster our molecules are moving. So larger number of those gas molecules are going to be about averagely in that higher speed range. Whereas the lower temperature, right, they're not moving as fast, so they're going to be more of those at that lower end speed of your distribution. Okay. So the taller the peak, the lower the temperature, or like the taller the peak, the lower the temperature. The other way you could see it is where you're given this. And you're given O2, N2, M2. And yeah, that's a good one. Cl2. All right, and you need to distribute them this way. What do we know about weight and speed of a molecule? Awesome, yep. So this is still average speed and number of molecules. And so which one's going to be the flattest, the heaviest or the lightest? The lightest. So out of O2, N2, F2, and Cl2, which one's your lightest? Does everyone memorize a periodic table? N2, yep. So N2 would be here. What comes next? O2 is, yep.
then have to then see them.
off to. Yep. Some of us. Right, so the flatter your peak is, depending on the type of question, right? All of these in this case would be at the same temperature. So if you're comparing different gases at the same temperature, the flatter it is, the lighter their gas is. If you're comparing the same gas at different temperatures, the flatter it is, the higher the temperature for that one. Okay, and that's a Boltzmann distribution. Multiple choice questions or like fill in the blanks, labeling a multiple choice or labeling a Boltzmann distribution is a good like quiz question or test question. Just wanted to introduce that and explain it a little bit. Alrighty, I think that's 6:30, so I will say farewell and thanks for coming. Hopefully that was helpful and I'll see you next week.
For all that, so we haven't done any of this.
Yep. I know it's a little hard to balance both of them, but